Welcome back to class 14. Here's the last example for this class. I swear there's been a ton of examples. I think I did like how many videos have I made for this? I don't know. Like 10 videos for this class. I went overboard. Anyway, here's the expansion of refrigerant R134A in a refrigerator. So this is a capillary tube, just a tube. A refrigerator has a saturated liquid at 0.8 megapascals and is throttled, right? So this is the throttling process. This is the throttling example. It's important to know that there's a throttling homework problem. So this is a throttling example. It's throttled from that 0.8 to 0.12 megapascals. And we want to determine the quality of the refrigerant at the final state and the temperature drop during this process, which is a really important thing. So I think this thing right here already gave us like information that we probably could have looked up as part of the thing. So let's ignore that and just do the problem. All right, so we take a look at state 1 at P is equal to 800 kilopascals, and P2 is equal to 120 kilopascals. And they tell us anything about the first? It's a saturated liquid, right? So this is saturated. So we're going to need to look up, and I'm not going to look it up in the book in this way. We could, all right. What you end up having to do for that is go to the tables for 134A. Come into here and you look for, first off, 800. You're not going to find it, right? Because they don't have a pressure indexed tables, unfortunately. So you would have to go in between here and here, and you need to be on the second page actually, where the enthalpy is. And if you go in between here and here, the saturated liquid is going to be this value. So it's going to be somewhere in between 241 and, am I right there? I think so. Somewhere between 241 and 249. Also, the temperature that you want is going to be somewhere between 666 and 771. Well, that's a whole lot of horse hockey. That's no fun. What we could do instead is go to this IRC thing, and I've already put it as 134, and for the pressure of 800. And now, but here's the weird one we have to do. I think we have to do quality, and I'm not sure if we want to do 1. Let's check it. Let's see what 1 is. That 100% or is that 0.01? That's saturated vapor. All right, so we want to go 0. Well, let me do for 0. Yeah, saturated liquid. You see it right there, saturated liquid. And what you get is the enthalpy. Here you go, enthalpy of not matching what I'm doing here. Look at that. One of those things in life that you just can't stand. You can't use this table for that and get the same values. It'll probably all work out in the end, because I got the same temperature. I got this temperature 31.3 exactly. But I did not get the same enthalpy. That stinks. Let's see. I'm going to write this down here over to the side and try this out. So H1 from IRC. I don't even know what IRC stands for. I should look it up. But it has a good name. I don't know what it is. I really don't know. I haven't gone to like this debate the website to see what it is. I'm sure it's something good. 995.501 kilojoules per kilogram. As opposed to what I was looking up for. I was looking for somewhere around 243. That's what I was looking for. 243. Like, there you go, there. Because this was saturated enthalpy liquid right there. it should have been somewhere in between there. Maybe somewhere in between here, actually, somewhere in between these two, because we were looking for 800. Yeah, in between right here. We ended up being 31 point something degrees, 31.24 degrees, but we didn't get the same thing, and I don't know why. I'm sure there's a really good reason. They're probably like this might have been, maybe this was updated. This was updated earlier, or the book was updated. I don't know. One of those two things probably. But I'm using the right thing. So anyway, if I go to the tables, I find and I interpolate. I'm not going to show you the interpolation. Tsat was equal to 31.24 degrees Celsius, and H1 was 243.61 kilojoules per kilogram. So I interpolated in between two values to get that. We're going to do the same thing over here. No. What we have to do now is we have to use the same enthalpy, because the throttling process, H1 equals H2. Right? The throttling process, as long as there's no loss, or assume there's no losses, so the enthalpy remains unchanged. And what we will find on the outlet of the thing is that at this pressure, where does that fall, right? And we can find out what the temperature is going to be at that state as well. So coming back here, we were at 120 kilopascals, which is somewhere in between here and here, right? And notably, so we would want to interpolate in between these two things, and then go back over and take a look at this. Here is the enthalpy in between these two here, and the enthalpy, here's the gas enthalpy, right? So here's the gas enthalpy, and here's the liquid enthalpy. So what we have to do is two sets of interpolations. What we will find, so I'll show you what I did. Two sets of interpolation. We have negative 25 and negative 20. And we find what the HF is, what the HFG is at those two, and then down here. And then we interpolate in between to get the pressure. We interpolate this guy right here to get the pressure. And then we find, here's what the temperature we're going to predict at. And here's the HF and here's the HFG. And then we can find out what the quality is going to be. So let me go back just a second ago. All right. So here's what we're saying, that if a state 2 has to be equal to state 1, right? No, I see. State 2. Oh yeah. Okay. So here is the state, right? So I interpolated up here for state 1. Here is what the H1 is going to be. It has to be the same enthalpy at state 2. But it has to be the pressure. So I don't have that pressure listed. So I have this pressure listed and I have this pressure listed. So I find it between 120 in between these things. So I've interpolated to find that this is the temperature that we would get in that corresponds to this pressure. And here is the HF that corresponds to 120. And here is the HFG that corresponds to 120. So now what I can do is I can find, well, what is the quality? Because you notice that it's well, not quite in between here. It's actually in between here and here. It's in between the gas ones, but I didn't bother doing those. So I can find what the quality is going to be right here. So let's do this electronically, because this is a pain in the ass, right? In this isenthalpic process. So because this didn't work, because this wasn't the same as this other one. Whoops, I'm sorry. I put up all my papers down. There you go. No, there you go. There you go. I wrote that one down though. Okay, so now we're going to find at P2 equals 120 kPa and H2 equal to 95.501. But remember that this IRC thing uses joules per kilogram. So let's look that up. Hopefully we'll get the right temperature and the right quality. I hit the wrong thing. Let's see. Boom. All right, so we have the opportunity using our 134 to go to 120. And now the enthalpy. The enthalpy. There you go. And so what did I say? 95,000. 95,501. And boom. And our temperature is not the same. No, it is. Yeah, I got negative 22.59, and they got negative 22.30. And the quality was 34%. And I got a quality of 34%. Okay, so in this instance, it's not so much fun to use the tables, but we can get them to match, and then we can be done, because I want to be done, and I'm done. Well, we'll see you in class 15.